Hello, thanks for joining our session. My name is Chris Carmona, and in this talk, I would like to present our work on scalable modular Bayesian inference with normalizing flows, and introduce a couple of ideas in the context of Bayesian data integration and model misspecification. This work is a collaboration with Jeff Nichols, and we're both based at the University of Oxford. Here are the main takeaways from this short talk. We propose a flexible and scalable approach to target modular posteriors based on variational inference and using normalizing flows. These modular posteriors are important because they allow us to reduce model misspecification arising from contamination between different modalities in a general model. However, sampling these modular posteriors is not simple, mainly due to its double intractable terms, which complicate things in settings where the number of modules is large. So it is computationally prohibitive to compare all possible configurations, reducing feedback from different modules. So we make a contribution on this direction, allowing to explore modular posteriors accurately and more efficiently. The talk is divided in 5 sections. I will start by introducing modular Bayesian inference and some of its applications. Then we discuss how the SMI and cut posteriors allow us to control feedback between modules. Then the core of the talk is at presenting how we can target these modular posteriors using variational inference. Then I will show you this variational approximation in action. And finally, we conclude discussing some considerations on this approach. So let's get started. We're interested in models that are made of several modules. We can illustrate such setting with this toy example, where we have 2 data sources, Z and Y, and let's suppose that we have a model for this data, which depends on link parameters, say phi, and module-specific parameters theta. This setting can be extended both horizontally for more datasets or vertically for hierarchical modeling. But let's consider this minimal example for clarity. We can perform Bayesian inference to learn simultaneously from all data and update our beliefs about the model parameters. The conventional posterior would be as shown here. This is a common setting in a number of real-world applications that seek to combine multiple data sources. For example, this diagram comes from a paper by Martin Plummer investigating the relation between human papillomavirus prevalence and cervical cancer incidence across different populations. In pharmacology, PK/PD models combine modules for the concentration of a given drug in the body with the physiological effects of that drug. In air pollution studies, some modules may correspond to the level of exposure of individuals to pollutants in the environment, while other modules correspond to health outcomes. Also, beyond biological applications, we recently collaborated with a team of archaeologists using a model that combines data from excavations in Mesopotamia with data produced in labs to discover some agricultural practices in early civilizations. There are also some models linking the spread of political ideologies with voting choices, and more recently, applications using geographically weighted regression, which considers data from different countries as separate modules. And well, many other applications. Now, a common aspect shared by all these examples is that they are interested in controlling the feedback between their modules during inference. There are several reasons to do this, but a particular one is to avoid model contamination, as some of the modules may be misspecified or some of their assumptions may be uncongenial, which could distort the inference of the model as a whole, leading to bias, incorrect variance estimates, poorly calibrated uncertainty, and other undesirable effects. A well-known approach to eliminate feedback from suspect modules are cut posteriors. For example, in our toy model, we can cut the feedback of Y into phi, so the posterior of phi is estimated with data only coming from Z. This modification sounds simple, but it induces an additional intractable term into the joint posterior, which complicates things later. Alternatively, another option to handle model misspecification is to use power posteriors, which reduce the relative importance of some likelihood assumptions in the learning process. Here we raise the likelihood of Y to the eta power. Recently, we proposed Semi-Modular Inference, which unifies these 2 approaches in an encompassing framework. The idea is to be able to tune rather than eliminate the influence of individual modules in the joint learning process, allowing to aggregate evidence while caring for model contamination. The semi-posterior is characterized by eta, the degree of influence of each module. In our AI stats paper, we discuss theoretical details of this framework, show that this is a coherent update of beliefs. We implement it using MCMC and discuss some ways to choose the optimal degree of influence eta. To clarify the idea, the semi-posterior can be represented graphically as an unfolding procedure and learning in a two-stage process. Using our working example, when I unfold this graph, I create an auxiliary copy of the parameters theta and the data y. In the first stage, we use this copy to learn the posterior of phi using a tempered version of the modules with the power posterior. And then in a second stage, we relearn the module-specific parameter theta conditional on the posterior for phi. Notice that the semi-posterior interpolates between the conventional fully Bayesian posterior when eta is equal to 1 and the cut model when eta is equal to 0, generating a family of inference procedures indexed by eta. Now, some challenges arise when we use modular inference. One is that sampling from the cut and the semi-posterior is not straightforward, mainly due to its double intractable terms again. There are new methods in the MCMC literature aiming at this issue, but in the general case with more than 2 modules, we often don't know which models to cut, and finding the optimal degree of influence of each module would be very demanding. Exploring such high-dimensional eta space would be very expensive using MCMC, as there is one posterior associated to every choice of eta. So we're interested in finding scalable approaches that allow us to effectively find and compare a large number of modular posteriors for a given model. Thanks to its computational efficiency, variational inference has become a commonly used approach for large-scale approximate inference and a natural alternative for tackling our problem. Such variational approximation entails finding the distribution that minimizes the KL divergence to the SMI posterior, given a variational family of distributions. However, it is not trivial to optimize the divergence directly because, again, modular posteriors have multiple intractable terms. For example, in the cut posterior, that P of y given phi term in red complicates finding the elbow analytically. So how do we do it? Well, we realized that the trick is done by following the same intuition as when constructing the SMI, using a two-stage approach. First, obtaining the marginal posterior to the link and auxiliary parameters, phi and theta tilde, minimizing the KL divergence to the power posterior, and then obtain the complete joint posterior by minimizing the conventional elbow, but freezing the part that was already learned. As a concrete example, suppose that our variational family is a full-rank Gaussian family, parameterized by mu and L, with L the lower Cholesky factor of the covariance matrix. In the first stage, we optimize the elbow to the power posterior by changing only the elements corresponding to phi and theta tilde, and in the second stage, we change the elements for theta. More formally, we need to define a variational family with a density that can be factorized as the product of 2 terms, each using a separate set of variational parameters, say alpha and theta. We will exchange the problem of minimizing the KL divergence to the SMI posterior for a 2-stage optimization procedure. First, approximate the marginal posterior for phi by varying alpha, minimizing the KL to the power posterior. And second, we get the complete variational posterior by minimizing the conventional KL, varying beta while keeping alpha fixed. In our preprint, we show why this procedure is an effective approximation to the SMI and cut posteriors. At each stage, we use stochastic variational inference and maximize the corresponding elbow using Monte Carlo approximations of its gradient. And moreover, using automatic differentiation, we are able to aggregate the 2 stages in a single loss function by stopping some gradients in the computation graph. So instead of maximizing the 2 elbows sequentially, one for each stage, we train the variational posterior end-to-end using this modified loss. which incorporates elements from the two elbows and indeed facilitates training. Now, the final ingredient is the choice of the variational family. So we propose to use normalizing flows as they offer remarkably expressive probability functions that can be used for scalable variational inference. Some of these flows in theory have the property of universality, meaning that the flow can learn any target distribution to any required precision given sufficient capacity and data. And indeed, we can define conditional normalizing flows that satisfy our requirements for modular inference. The idea is to define a base distribution as well as two transformations, G1 and G2, which are invertible and differentiable. Then transforming the base distribution using G1 and G2 will define our variational family. Phi is produced by transforming epsilon1 and theta is produced by combining phi and its own epsilon. The conditional distribution of the transform variables define our variational posterior, and it is given by the product of the base density and the Jacobian of the overall transformation. Again, the parameters to optimize here are alpha and beta. In our experiments, we have obtained very positive results using inverse autoregressive flows, obtaining fast and accurate convergence even for high-dimensional posteriors. These flows are based on autoregressive neural networks that sequentially transform the elements in epsilon, so the Jacobian of the matrix of the transformation is lower triangular. In most applications, a final transformation is required to map parameters to their specific domain. For example, soft plus for positive parameters or sigmoid for probabilities, and so on. Now, I'd like to show you the method in action. We have tested the framework in a number of different examples, but here I show you the results for the well-known epidemiological study by Plummer relating papillomavirus prevalence and cervical cancer incidence. The dynamics in the plots illustrate various degrees of influence, going from 0 to 1. This is from the cut posterior to the conventional posterior. In the bottom panel, we show the estimated relation between the rate of cancer incidence on the y-axis versus the virus prevalence. Each color is a different group under study. The upper right panel shows the slope and intercept in the model. These are the theta in our diagram. These posteriors are using inverse autoregressive flows, and we can see that they exhibit some complex shapes that couldn't be captured by more traditional families like mean field or full rank Gaussian. The execution time is also significantly faster compared to MCMC, and yet we obtained very good approximations to the SMI posterior. As a comparison, here we show the results of using mean field, which certainly underestimates posterior variance. Now, to conclude, the approach we presented here might allow for faster exploration of many modular configurations for a given model. Some flows facilitate the definition of expressive default variational families, which are able to target complex posteriors, even with many models. A promising extension of this approach is using meta-learning to find parameters that are good for many influence rates. Of course, many studies on convergence rates of normalizing flows are needed, but recent advances in robust variational optimization provide diagnostics for convergence and stopping rules during training. Code for these and other examples are available in my GitHub and reproducible using Google Colab. Well, thank you for your time and interest, and please feel free to contact me if you have any question.